Lecture number 10, the mole. So in the last chapter we talked about atoms and combined those atoms into molecules and then talked about how to name those molecules. But in this chapter, starting in chapter 3, we're going to start taking that leap again from this microscopic world of atoms and molecules into the sort of the world we operate in, this macroscopic world where we're dealing with grams and volumes. So the first step we took already was talking about this atomic mass based on the mass of carbon-12 ion. Remember that was one atom of carbon-12 had a mass of 12 AMUs. We've got all of those. We can now then expand on that. Instead of talking about single atoms or molecules, talking about a large group of those atoms and molecules, which we're going to define as a mole. And a mole is the amount of a substance that contains as many elementary entities as there are in atoms in exactly 12 grams of carbon-12. So again, all of this idea is based on this one isotope of carbon. And we find that the number of atoms in 12 grams of carbon is this very long number, 6.022 times 10 to the 23rd atoms, which we refer to as Avogadro's number. Right? So that 1 mole is defined as anything having 6.022 times 10 to the 23rd things. Right? We can talk about anything we want. It's defined as the carbon atoms, but it's really just sort of what we call the chemist's dozen. So if we have, it's that number of things, right? Avogadro's number. So then we can talk about a molar mass, the mass of 1 mole of these, but it could be anything. We're going to talk primarily about atoms or molecules in class, but really it's anything. It could be eggs, shoes, whatever. So then we can talk about 1 mole of carbon atoms, which would be Avogadro's number, 6.022 times 10 to the 23rd atoms, is equal to 12 grams. Right? We do that same thing with all of them, but we see that for all the elements, their mass is equivalent in either AMUs or grams. So hydrogen is going to have a 1.008 AMUs mass, or that'll be 1 mole of hydrogen is 1.008 grams. So they're equivalent. So then having this idea where we have this molar mass, we can then convert between anything. We can take a mass of an element and figure out the number of moles of that element is present. Right? Or if we have the number of moles, we can go back to the mass through this molar mass. And if we have the idea of the number of moles, the quantities there, we can talk about the number of individual atoms using Avogadro's number. So now we can convert from elements, from mass in grams, to this atoms using this molar mass and this idea of the mole. So when we talk about, we don't talk about individual atoms necessarily as this large collection, this mole of atoms. And we can see one example of that where we can see how much an AMU weighs here in this example. And we can just do the unit conversion, dimensional analysis, same as we've done before, and get this to work out. So we can define a molar mass then as that atomic masses of the molecule in either AMUs or now in this grams per mole. So again, if we look at carbon dioxide, we have 2 oxygens, each one of those is 16 AMUs or grams per mole, and 1 carbon, 12.01 AMUs or grams per mole. So it gives us a molecular mass of 44.01 AMUs or 44.01 grams per mole. So again, we can talk about this as this mass as an individual molecule. We use AMUs, or 1 mole of these. Then we use this molar mass of grams per mole. Interchangeable. Right. So this idea of a mole is going to allow us to convert anything. So now if we know the number of atoms present or a mass of a compound, we can then get all that other information. If going through this moles or the molar mass, we can figure out how many moles are there from that mass, which we can give us the number of molecules that are present or the number of elements that are present. So our compounds are not only going to be a relationship of this number of atoms, but we can also talk about the number of moles of those atoms. So let's take that one step further and talk about this percent composition or percent by mass that we've talked about before. So we can take that, just like we've always done, the number of atoms present times their mass divided by the total molecular mass or molar mass. So before we've used it in AMUs, now we can use it in this new unit of grams per mole. where N is just the number of those present. So if we look at this molecule C2H6O, we can figure out the percent composition or percent by mass for each one of those by taking the number of them present. For example, a percent of carbon is going to be 2 carbons present times their mass of 12.01 divided by the whole molar mass, which is 46.07, times 100, we get 52.14. Right? So every time we get this molecule, we're going to have those masses. Right? So we can talk about the same process we've done before. What this really leads us to is if we have this information, this percent by mass, we can then determine the empirical formula by going through this moles. So if we take these percentages, if we assume a certain mass, say 100 grams of this compound, then that percentage just becomes a number of grams. If we then figure out how many moles are present in that mass, we can then figure out how many moles of each one of those are present. If we then divide by the smallest to get the smallest whole number ratio, divide by the smallest number of moles, that gives us the relationship of each of those atoms in that molecule. So we can see that in this case our empirical formula based on this molar smallest whole number ratio of moles is going to be C2H6O1. So if we have the formula information about the molecular formula, then we can take this simple whole number conversion based on the molar ratio to get from the empirical formula to the molecular formula. So we're just going to take that molecular mass, the one that we know, divided by the empirical mass that we just found. So for example, if we have a molecular mass of an unknown is 90 grams per mole, and the empirical formula we found was NO2, then we're going to take that 90 grams per mole for the molecular mass, divided by the molar mass of the empirical formula, NO2, which would be 46.01. Divide those two together and we get a number that's approximately 2. So in this example, we can take that molecular formula to be N2O4, twice the number of that empirical formula. So now, from this idea of the mole, right, we can now start making pronouncements about how we can operate in grams. So we can now follow through the molar mass and this idea of the moles interacting to actually do some more complicated interactions and allow us to start talking about chemical reactions. So we'll begin talking about chemical reactions in the next lesson.
Dad, I done did it.